Good afternoon, everyone. Today we are going to discuss about the risk assessment of sustainability initiatives in Saudi Arabia. First, I would like to introduce our team. Under the esteemed supervision of Professor Mr. Vikash Ramya, we have Paul Hooper, Beste Rauda, and Muhammad Hadi. Hello everyone, my name is Pearl Duper. Today we'll delve into the potential risk associated with the key energy initiatives critical for Saudi Arabia's Vision 2030, particularly focusing on how to mitigate them for a successful implementation. The objective of our report is to assess the risk management framework of the proposed sustainability energy initiatives using risk register, risk matrix, and capital expenditure and operating expenditure. Solar PV is vital for economic diversification, cutting emission, and enhancing energy security. It also creates jobs and lowers fuel costs. Its key brands include ACWA Power, Jinko Solar, and Trina Solar. The LED lighting improves quality of life and safety and enables smart city. The top brands include Shadar, Signify, OSRAM, and Xiongto Bell, offering solutions like Avento streetlights and Shuffle smart poles. We'll start by doing a risk analysis using risk register and risk matrix. Comprehensive risk register systematically identifies potential challenges for each energy initiatives. Each risk has a clear mitigation strategy to reduce its impacts and likelihood, such as using certified long-life products or implementing secure protocols. Our analysis shows the initial risk distribution with significant number of risks having high likelihood and impact. However, with the proposed mitigation strategies, we project a substantial shift towards a low and moderate risk profile as shown by the post-mitigation distribution. Now we'll talk about the cost analysis of energy initiatives. To put these initiatives in perspective, a medium-sized solar plant with installed capacity of 1 to 20 megawatts has a total capex around 62 million Saudi riyals and an OPEX of approximately 9,40,000 Saudi riyals. For LED lighting, a project involving 50,000 fixtures might incur a total capital expenditure of 10 million Saudi riyals. With an annual operating expenditure of about 5 lakh Saudi riyals for routine maintenance, cleaning, and minor replacements. This chart visually summarizes the distribution of risk across our energy initiatives. Solar plants and PV rooftops, along with thermal insulation, currently shows the highest number of identified risks, indicating where our focus on mitigation will be most critical. These charts provide a quantitative summary of our risk. The first chart shows how the average likelihood and impact have been substantially reduced. The high risk count has dropped to 0 and the moderate and low risk counts have increased, signifying a healthier risk profile. The next chart clearly illustrates the before and after average risk scores for each initiative, emphasizing the significant reduction achieved through our tailored mitigation strategies. Now we'll discuss about the potential risk for energy initiatives in brief. Our first risk is grid integration. A primary risk here is increased operational cost for grid operators and potential grid instability leading to blackouts. To mitigate this risk, Saudi Arabia needs significant investments in smart grid technologies through implementing advanced grid management systems or forecasting tools, or use of hybrid power plants with thermal storage for backups, or lastly deploying utility scale battery storage, example lithium ion batteries to store excess solar power and release it when needed. The total cost of lithium storage battery for a medium sized plant with solar capacity of 1 megawatts to 20 megawatts designed for storage of 2 to 4 hours of duration can range up to 660 to 1095 Saudi riyals per kilowatt hour. Next, for solar capacity, a risk is losing solar power output annually and underperformance against financial projections due to panel degradation. Our solutions include stringent quality control, sourcing from reputable manufacturers, and regular performance monitoring, and crucially, using sun simulators for consistent panel testing. A solar simulator is a specialized laboratory or factory device designed to reproduce the natural sunlight spectrum and intensity for the purpose of testing solar cells and modules. This helps determining a solar panel's electrical performance under standard test conditions. Manufacturers can use them to ensure panels meet specified performance criteria before shipping. Solar simulators can be classified as Class A, B, and C based on their accuracy. Basic Class C and B simulators can range approx 73,000 to 3,67,000 Saudi riyals. However, the high precision Class A simulators can range from 7,35,000 to 3.67 million. Water intrusion poses a significant risk to the inverters, leading to failure, downtime, isolation faults, and component degradation. The mitigation involves selecting higher IP-rated inverters, specifically IP66 for desert storms or IP67 for flood-prone areas, alongside proper mounting and regular inspections. Lastly, a typical IP-rated inverter for a medium-sized plant costs approximately 2,000 Saudi riyals each. Dust accumulation in our desert environment causes efficiency reduction and proportional loss in energy production and revenue. Our solution is twofold: implementing auto-robotic cleaning systems and applying anti-soil coatings. For a medium-sized plant, anti-soil coatings could cost between 1,69,000 to 4,22,000 Saudi riyals. Cracks on solar panel reduces power output efficiency and can void warranties. The solution includes using enhanced glass, ensuring International Electrotechnical Commission certification, and utilizing electroluminescent solar module tester for inspection, with a tester costing approximately 6,000 US dollars. The EL Solar Module Tester is a crucial diagnostic tool used to identify hidden defects in solar panels that are not visible to the naked eye or through standard visual inspections. It's particularly effective at detecting tiny cracks in the silicon cells, which significantly reduces efficiency and leads to hotspots. It clearly shows broken cells and also reveals any poor electrical connection. Lastly, it also helps in identifying problems like dark cells, which are non-functional areas, and various manufacturing defects. The tester works by applying an electric current to the solar panel. When electric current flows through the healthy PV cells, they emit light in the infrared spectrum. This IR emitted light is then captured by the high-resolution specialized camera. The captured EL image acts like an X-ray of the solar panel. High temperatures lead to degradation of solar panels and inverters, resulting in revenue losses and daily power losses due to overheating. Mitigation involves selecting high temperature resilient panels, optimizing mounting and ventilation, and deploying advanced cooling systems for inverters, complemented by the use of sun simulators. Cybersecurity are a critical risk, potentially causing operational downtime, significant financial losses, reputational damage, and grid stability risk. Our defense includes implementing robust cybersecurity architecture, conducting regular audits and penetration testing, and investing in continuous employee training and awareness. Specific to LED lighting, a major risk is operational failure and reduced energy savings due to lumen depreciation or sensor failure caused by harsh environment condition and dust. This leads to degradation, loss of brightness, and reduced output. Mitigation includes deploying automated cleaning systems and specifying certified long life, robust X-proof LED lights designed for extreme conditions. These LED lights are built with high strength, corrosion resistant material to withstand the harsh conditions. LED technology provides bright illumination with low energy consumption, reducing operational cost. It is designed to minimize the heat emission, reducing risk of overheating. Lastly, it's built for longevity, reducing maintenance frequency and cost. Lighting also carries the risk of light pollution impacting human health and ecosystems. Our solution is intelligent lighting design and fixture selection, emphasizing shielded and directed light like the Shadar Evento street lighting solution to ensure light goes only where it is needed.
Today, I'll present our key findings on material sustainability initiatives in Saudi Arabia. As part of our risk management analysis, I focused on three critical materials initiatives that align with Vision 2030 and offer significant environmental benefits. Let me start with our three core initiatives. First, recycled steel using electric arc furnace technologies with scrap metal versus 4 to 48% reduction cost versional steel and 70% COD or emission percent condi emissions reduction. The Saudi scrap export ban ensures reliable local supply. Second, recycled concrete involves reusing demolition waste as aggregate. Has IRC Invest has in 160 million SAR in this sector, achieving 5 to 10% COE reduction with optimal performance using 25% recycled concrete aggregate. Third, local sourcing targets the 160 plus billion-dollar Saudi building materials market and reducing transport emissions by 0.05 to zero point 0.1 tons COE per ton. While it has strong Vision 2030 government support, we face supply capacity constraints that need addressing. Our risk analysis identifies key challenges across all initiatives. For recycled steel, market price volatility is mitigated through long-term supplier contracts and hedging mechanisms. Quality inconsistency risks are managed through enhanced quality control systems and supplier certification programs. Local sourcing faces supplier capacity limitations, which we address through development programs and capacity building initiatives. Recycled concrete processing costs are managed through economies of scale and technology advancement. The financial structure shows recycled steel requiring 50 million CRTPX with 50 million annual OPEX, delivering strong returns. Local sourcing needs 75 million TPX for supplier development with 20 million OPEX. Recycled concrete requires 35 million TAPX for processing equipment with 18 million annual operating costs. Total portfolio investment is 160 million CAR, generating substantial positive NPV. Our comprehensive risk register contains 18 detailed risks across all initiatives using a 1 to 5 scale for likelihood and impact assessment. The risk makes visualization shows most risks are medium level and manageable through our mitigation strategies. High priority risks include market price volatility for steel, supplier capacity for local sourcing, and processing costs for concrete. Our color-coded system helps prioritize mitigation efforts effectively. Beyond risk mitigation, we've identified significant opportunities. For recycled steel, the 44 to 80% cost savings creates competitive advantage in construction bidding and improves project profitability. The 1.6 tons COV reduction per ton creates potential for carbon credit revenue as the Saudi carbon market develops. And local sourcing supports Vision 2030 economic diversification goals by developing domestic manufacturing capabilities, creating jobs for Saudi nationals, and building supply chain resilience by reducing import dependency. Recycled concrete addresses 60 million tons annually of construction and demolition waste, creating new revenue streams. The NovaScript consortium positions Saudi Arabia as a leader in sustainable concrete technology development. Our key findings show Korea Steel offers high savings, 70% CO reduction, and high implementation readiness, making it our priority initiative. Recycled concrete currently has a cost premium but provides significant waste management benefits with strong long-term potential. Local sourcing has strong Vision 2030 alignment but faces supply capacity constraints requiring strategic development. The overall risk profile is medium risk with high potential returns. Importantly, all initiatives meet green finance compliance under the green buildings category, achieving 45% COE reduction, supporting Saudi 2030 targets, and aligning with UN Sustainable Development Goals 9, 11, 12.
Hello everyone, thank you for joining me. I'm Mohammad Hadi and I'll be presenting this assessment of sustainability initiatives and my focus would be on mobility. So firstly, let's go through the executive summary of my assessment. So this report consolidates the major risks associated with implementing the mobility initiative across the Kingdom of Saudi Arabia. So as our objective is to assess the risk management framework of the proposed sustainability mobility initiative, and we will be using risk register, risk matrix, and capex and opex. So the initiatives which we are going to assess are EV charging, walkable city, micromobility, and public transport. Let's move on to our introduction. So, why are mobility initiatives important? So, firstly, it aligns with Vision 2030. So, Kingdom of Saudi Arabia has a Vision 2030 which calls for diversifying the economy, even enhancing quality of life and reducing dependence on oil and mobility initiatives are cornerstone to modern infrastructure to promote sustainable cities, even improve public health. Then we have environment sustainability, in which mobility initiatives such as EV, micromobility, and walkable public transport, they will all reduce greenhouse gas emission and air pollution and enable fossil fuel consumption. Then the traffic congestion and urban efficiency. So there are major cities like Riyadh and Jeddah which face growing congestion due to urban sprawl and car dependency. So the public transport and walkable infrastructure would really help to ease the congestion. And then there's public health and livability, where active mobility options would improve population health and encourage social cohesion, such as like uh, encouraging walking and cycling. As we can see, these all has benefits. So, firstly, our carbon emissions are going to be reduced, and there's going to be job creation, and in the transport services, even clean tech and maintenance. And then there we are also trying to boost non-oil GDP through transport, tourism, logistics, and innovation sector. Then it will also improve the public health, as I said before. via walking. It will encourage walking and cycling. So moving on to my risk analysis, I'll be discussing two components in this part. It will be risk register and risk metrics. Quickly, so this here is the risk register for all my four initiatives. The risk IDs, you can see the risk with R represents the EV charging, risk with W represents the walkable city, M represents micromobility, and P represents public transport. So here I have risk IDs, risk descriptions, and then likelihood and impact, and then their mitigation strategies. Then I have post mitigation strategies, and then we can also see the initial and post mitigation risk score and also differentiate in that. So this is my risk matrix. We can see that the red colored number 6 is basically the critical risks, the high risks, number 13 and 8, the yellow colored numbers are medium risks, and num green colored number 10 is low risk, so which has very less impact and which is not important to be treated. The red risks are critical to be mitigated, and uh, they should be treated very timingly. Moving on to the next part, let's discuss the cost analysis of mobility initiatives. So this right here is capital expenditure for EV charging. So the top right graph shows us the baseline assumptions that we are going to install a 10,000 chargers, and which would be 70% would be level 2 charger and 30% would be fast charger in 40 major cities plus intercity corridors over the period of 5 to 7 years. And on the left, the graph shows us each component of the capex per station. So, and then we have nationwide capex estimate, which shows us that the total will cost us around, if it's uh, cost us around 1.05 billion to 1 point estimated 1.05 to 1.55 billion Saudi Riyal. So on the bottom right, I have put a three-phase plan for 7 years, which also shows us we shows us the unit we have to purchase per year uh, according to the phases, and then it also shows us the lowest total capex and the highest total capex, which is 1.045 million billion to the highest is 1.5 billion. So this is OPEX for EV charging. So the top left graph shows us the categories and on which we are going to decide the cost. And then the chart parallel to it, the table parallel to it basically shows us the total cost. So as I said before, you're going to use 70% of level 2, which is 7,000 level 2 charges and 3,000 DC charges. And we have annual OPEX cost range, and then we can calculate the total annual OPEX range, which is from approximately 145 million to 204 million Saudi Riyal. I've also put in the three-phase plan to complement the capex, and this also shows us that in phase one, our cost is going to be, if it's lower, it's going to be around uh, 65 million, and highest is going to be around 93 million, and the total lowest cost which we are going to face is 352 0.5 million to 495 million. So this right here is capital expenditure for walkable city. So first we can see that there are key walkable components, each listed differently, and then we can see the capex summary table. So this is basically for 500 kilometers. I've assumed that I'm making a walkable network across KSA for 500 kilometers. So this cost is for that, and we have a low estimate and a high estimate. So the total capex cost for making a walkable city in King Saudi Arabia of 500 kilometers is varies from 1.53 billion Saudi Riyal to 3.48 billion Saudi Riyal. So here is the OPEX for walkable city, and we can see each component separately with cost Saudi Riyal per kilometer per year, and also total for 500 kilometers. The details for each component is also given, like what type of maintenance, for example, inside when pavement where there can be cleaning, patching, or even leveling. So the annual OPEX summary for 500 kilometers, the lowest estimate is 71.5 million Riyal, and the highest is 113.5 million real. So this right here shows that we are going to the the OPEX for different cities like Riyadh, Jeddah, and Dammam. So we need to make 200 kilometers of walkable track in Riyadh. What is it going to cost, the OPEX? And it even shows the each cost of different components and the low and high cost. So we can take a look and plan accordingly. So this is capex for micromobility. As we can see in the breakdown of components, we are purchasing like 30,000 units of e-scooters and 20,000 units of bike, which is a fleet of 50,000 vehicles. And we can see each component separately with its units and total cost. So the total cost for capex would be, if we have a minimum estimate, it would cost around 418 million Saudi riyals, and the higher estimate would say 633 million Saudi riyals. So this is operational expenditure for micromobility, where we have different categories and cost per unit and fleets per unit and total annual cost, which will be around the lower estimate is 112.5 million real and higher estimate is 174.5 million real. Also, I have given note in the component table to understand the categories. So, for example, this vehicle maintenance. So we have like parts, labor, software updates. Same goes for battery charging. We have electricity, labor, logistics. I've also given a city plan where we have like 10 cities. So I've included like big three cities, Riyadh, Jeddah, and Dammam, and allotted vehicles to it, also the stations. And then we can differentiate in the total OPEX cost for low and high. So this is capex for public transport. So we are going to target 10 major cities with 6,000 buses and 40 to 50 major depots with ticketing, GPS, and fleet management. So then there's breakdown where there's each component and per unit cost and the total units and the total cost. So the total capex cost is going to range around uh, capex cost for public transport is going to range around 11.7 billion Saudi Riyal to 16.95 billion Saudi Riyal. So lastly, this is OPEX for public transport. So we have different components like driver salaries, fuel, energy, maintenance, depot, and breakdown individually. And the total annual OPEX cost would range around 125 billion to 1.7 billion Saudi Riyal. And then I also have a city plan where in Riyadh, suppose you're gonna purchase 2,000, deploy 2,000 buses with 15 depots, and they're gonna be 1,500 stops. So the total cost would be around uh, 3 billion Saudi Riyal, and the higher cost would be 4.8 billion Saudi Riyal. Also, we can see this annual OPEX cost for which is for both ranges low and high. Thank you. Moving on to my next part, findings. So first, this diagram shows box plot of initial versus post mitigation risk scores. So we can see the left box for the initial risk score, median lies around 20, the interquartile range is wide, and the middle of 50% of scores span roughly from 15 to 25, showing high variability. And then you see the second box, which is post mitigation score. You can see the median is around 10, which is a significant reduction. Even the IQR, which is interquartile range, is narrower and showing reduced variability and tighter risk control. This bar chart represents average risk score by category. The yellow chart shows, so there are three basically categories: financial, operational, and strategic. And the yellow chart shows the initial score, and the orange represents the post mitigation score. So we can see there's a significant decline in risk score after the mitigation in every category. So this bar chart represents total cost which is required to mitigate the risk according to their categories. So we see that operational risk requires the most cost to be mitigated. As we can see, it's more than 1,000 millions of the reals, and then strategic is the lowest around, which requires around 300 million reals, and financial requires around 650 million reals. We will be discussing key observations. So, firstly, operational risks were the most frequent ones, which also required robust projects and traffic management strategies. And then there were three risks R3, W2, and M2, which remained even high after mitigation. And further, we will be discussing how to mitigate this risk and cost required to mitigate these risks. So, moving on to my final part, let's talk about potential risk for mobility initiatives. Let's talk about my first initiative, EV charging. Basically for risk R3, which was a critical one, so as EV adoption increases, the demand for electricity will surge, especially during peak hours. If the grid is not prepared, this could lead to blackouts, voltage drops, or inefficient power distributions. So in order to mitigate it, we had to collaborate with utilities for capacity planning and infrastructure upgrades. So in order to do that, we could deploy smart charging solutions that manage charging off-peak hours and balance loads. Also invest in grid monitoring storage solutions, for example, backup batteries or even demand response system. As you can see, in order to mitigate this uh, risk, estimate of 3.0 million Saudi Riyal is predicted, which includes grid impact, smart charging software, limited infrastructure reinforcements, and partner development with utility companies. So for the second risk, as we know that the EV charging networks become digitally connected, they become target of cyber threat attacks and disrupt services, steal user data, or compromise national energy infrastructure. So this was also a 25 rating risk. In order to implement it, we had to use end-to-end encryptions, regular security audits, firewall, and intrusion detection system. So for mitigation, 2.4 million SA Saudi Riyal was expected, which included security audits, hardware and software security tools, cyber security training for operators, and monitoring and response infrastructure. So this right here is Walkable City, my second initiative, and it had only one critical risk. So as we all know that in Saudi Arabia, there's extreme heat, like often 45 degrees Celsius, and intense sun exposure with occasional sandstorms, which can make outdoor walking very uncomfortable or even unsafe for extended periods. So this undermines public use of pedestrian infrastructure, reducing the return on investment and defeating the purpose of sustainable urban mobility. So in order to mitigate that, we have different components like shaded infrastructure, heat reflective pavements, misting and cooling elements, urban lighting, and climate designs. Have also the cost range is also per kilometer, and the total cost is for 500 kilometers. So in order to mitigate this risk, we the in expected cost is around 425 million to 1.095 billion Saudi riyals. So this cost ensures the walkability is viable year round, even during peak summer months, and it is critical to be adopted in KSA. So moving on to my third initiative, micromobility, it also had one critical risk. So in fast-growing Saudi cities like Riyadh and Jeddah, urban streets are dominated by high-speed vehicle traffic. Include introducing micromobilities like e-scooters or e-bike would without protected infrastructure could lead to accident risk, public fear, and low adoption, even liability issue for operators and opposite from road users and regulators. So in order to mitigate it, we could build protective lanes, establish clear road signage, and enforce tech. Also, we could use public safety campaigns and training. Also, we could use policy framework and traffic law integration. So I've also put costs for each initiative per kilometer and the total cost, which is around 1,000 kilometers in micromobility lanes, and it is also rolled out in 10 major cities. So moving on to my last initiative, which is public transport. So this had two critical risks. So firstly, talking about P1, which was low public usage due to cultural preference for private vehicles. So we know that Saudi has a long-standing car-oriented culture, which is enabled by low fuel cost and road-dominant urban designs. Also, there's a social preference for driving. So without strong incentive or public appeal, public transport would remain underutilized despite infrastructural investments. So in order to mitigate these, I have given different mitigation components. So you can run national awareness campaigns, then launch mobile apps and real-time info systems. Also use TOD policy and pilot sites in 5 cities. So TOD is transit-oriented development. And then we could use service level agreements and bus optimization. And also the cost associated is written there. And then for the second risk, P3, which is high capital and operational costs with slow return on investment. So we know that there's large upfront investments in fleet and infrastructure, and operations may not yield quick returns. So public transport in early phases may run a deficit. Without proper planning, this might become fiscally unsustainable. So in order to mitigate, we have PPP and legal framework development. For example, like diversified funding from government, sovereign fund, World Bank. And then we have a long-term sustainability buffer for the first 5 years. Then we have commercial space integration at 100 terminals. So we can use phase scaling. We could start with high density corridors and then we could expand them later. And then there's advertising and branding setup, and also the cost associated is written with it. So lastly, for recommendations, firstly, you could prioritize mitigation for high impact and high likelihood risk, like risk ID R3 and P3. Then you could expedite regulatory reforms and planning approval for public transport and micromobility. Also secure long-term funding mechanism, especially for heavy capital items like public transit and charging infrastructures. Then you could use public awareness and incentive programs to drive model shift away from private vehicle dependency. And then lastly, you can monitor and update mitigation strategies regularly with performance data and community feedback.
Hello, I'm Rodal Shaybani. Today I will walk you through our financial and environmental evaluation of two water efficiency initiatives under the PIF Green Finance Framework. We evaluated alternate water use and efficient water appliances to compare CapEx, OpEx, and payback, model potable water and CO2 e-savings, and align everything with PIF's risk framework. In summary, we built a spreadsheet model to capture CapEx, OpEx, and payback, quantified water and CO2 e-savings, and scored every risk in a 5 by 5 matrix with defined mitigations. Here are the two initiatives I will discuss. Under Saudi Arabia's Vision 2030, potable water use must fall by 20%. Yet our municipal buildings still rely 100% on energy-intensive desalination. Today we will explore two targeted solutions: grey water reuse and Energy Star appliances, through cost-benefit analysis and a risk framework to ensure both financial viability and environmental impact. We reference the PIF framework. It sets thresholds on CO2 e-abatement cost less than 2,500 Saudi Riyal and requires a robust risk management process. For alternate water use, we modeled CapEx and OpEx and calculated payback, converted water savings into CO2 e-abatement, scored risk and defined mitigations. The tools used: our spreadsheet, risk matrix template, PIF checklist. For efficient water appliances, we modeled CapEx, OpEx, and payback, quantified water and energy savings to CO2 e-abatement, scored and mitigated supplier and user acceptance risk. For tools used, we used spreadsheet model CapEx, OpEx, and payback, risk matrix template 5 by 5, PIF Green Finance checklist. On our findings slide, you can see the financial and environmental outcomes for each initiative. Alternate water use requires a capex of 4.33 million Saudi Riyal and annual OpEx of 0.28 million Saudi Riyal, yielding roughly 2,900 tons of CO2 e-abatement over 15 years. That delivers a payback period of about 15.5 years. Efficient water appliances requires a capex of 1.995 million Saudi Riyal and annual OpEx of 0.105 million Saudi Riyal, yielding about 950 tons of CO2 e-abatement and a payback period of roughly 19 years. Both initiatives comfortably meet the PIF Green Finance of a 20-year payback, demonstrating they are financially viable and deliver meaningful environment impact. On this slide, you can see the detailed cost breakdown for the grey-water reuse system. And here are the costs for replacing old washers and dishwashers with high-efficiency units. On the appendix slide, you will see three supporting sections: key extract from Vision 2030, PIF guidance and vendor codes, our core assumptions on system sizing, tariffs, carbon factors and finance, and the exclusions like network losses, tariffs changes and user behavior that we have scoped out. These ensure full transparency behind our analysis. We identified 30 tailored risks across the five water measures, scored them for likelihood and impact, and proposed mitigation actions for each. This is our 5 by 5 heat map before mitigation. Residual matrix shows most risk shifted from high to medium and low after our mitigation measures, confirming their effectiveness. Here is the breakdown of average risk scores per initiative, before and after mitigation, highlighting which initiatives still need close monitoring.